Okay, so let me do this, and the next three questions as a group of four questions, they all should be a relatively simple Newton's second law question. So let me start by writing down Newton's second law. Newton's second law. As a reminder, both to myself and those of you watching this video, you can state it in two different ways, I guess. You could say net force is equal to mass times acceleration, or sometimes when I want to be extra clear what the direction of causality is, I will say acceleration is equal to net force divided by mass, because it's the net force that causes acceleration, not the other way around. But algebraically, these two things are equivalent to each other. So I'm gonna be using it. Let's read the question. It says, oh wait, I need to scroll up. The weight of an astronaut plus his spacesuit on the moon is only 270 newtons. Oh, how much does the suited astronaut weigh on Earth? I don't know. I think I wonder if you are supposed to look things up. Now you could look things up. You could search like what is the gravitational acceleration on moon. You could search, and I think I remember that's supposed to be like 1/6 of gravitational acceleration on Earth. So if I take this in meters per second squared. Let me just double check. If I multiply this by 6, is it close to 9.8? Not close enough for me to have used. I think that might be off by more than 1%. But let me use it this way. So I'm gonna, since Wolfram Alpha is able to look up constants for me, I'm just gonna use this. And otherwise, you'll be looking it up in the textbook or Google searching. All of those are fine. Let me answer part B first. What is the mass on the moon? Well, that weight, it's kind of related to the Newton's second law. What all that weight means is if there's the only force acting is gravity, then the acceleration would have been the gravitational acceleration on moon. So if I take the weight, the force, divided by the mass, so let me, acceleration. So this is the kind of the version of expression I'm working with. If I say, give the gravitational force that's given, I'm gonna call that net force for now, and I divide it by the acceleration they would have if gravity is the only thing acting, then that's equal to mass. And I guess you can't really divide the vectors by vectors, so let's say I'm just working with the magnitude, and it's just the net force magnitude divided by the acceleration magnitude. So I can do 270 newtons divide by this constant that Wolfram Alpha is going to look up for me. Then I get, why am I getting pounds? Kilograms, 166.3 kilograms. I guess the equipment must be fairly heavy. Yeah. So once I know I have the correct mass, then I can do the rest of the questions. Oh, the mass on Earth, it's the same mass. But on Earth, the weight will be different. The gravitational force on Earth is the mass times gravitational acceleration on Earth, or 9.8 meter per second squared. So since here I have the mass here, I need to multiply by 9.8 meter per second squared. That'll give me the weight on Earth. So 1630 newtons. Pretty easy question. As I said, these are all the group of questions where it's pretty simple application of Newton's second law. Let me get to the next question. All right. Suppose the mass of a fully loaded module in which astronauts take off from the moon is some mass. Okay. The thrust of the engines is some force. Okay. Calculate the module's magnitude of acceleration in the vertical takeoff from the moon. Okay. All right, so I gotta work this out. So whenever you are dealing with the situation, dealing with the forces, I recommend drawing a free body diagram just to make sure you have a correct mental image of the situation here. So for this fully loaded module, what they've given us is the thrust force. So there's gonna be an F thrust of 2.4 times 10 to the 4 Newton. Now, if you're trying to answer this question based on this, do this, divide by the mass, plug it in as acceleration, it'll say it's wrong. Because there's another force that's supposed to be on this module that's only implied from the phrase from the moon. So you have to take into account gravitational force from moon. Once you work this all out, then you write down the net force equation. Net force. Let's say upward is positive. I'm gonna assume the thrust force is enough to get it to accelerate upward. So it should be F thrust minus gravitational force from moon. That should be equal to mass times acceleration. So what I'm gonna do is I'm gonna calculate this divided by the mass that they gave us, and that'll give me the acceleration. Let me do the rest in Wolfram alpha, mainly because I know Wolfram alpha can, because the gravitational acceleration from the moon, that's gonna be mass of the thing, which we know, great, times not the usual g of 9.8 meter per second squared. It's gravitational acceleration from the moon. And although I remember, again, it's like about a sixth of Earth gravity, but I don't think that's precise enough. So I'm just going to use this constant that I know Wolfram alpha will look up for me. Let me build the rest of the expression here. The thrust force is 2.4 times 10 to the 4 Newton, and then minus the amount of mass, 2.8 times 10 to the 4 kilogram, times the gravitational acceleration on moon. That should give me the total force, net force, divided by the mass. 2.84, sorry, not 84, 2.8 times 10 to the 4 kilogram. So that should give me something in acceleration. Let's check. Think it understood me correctly. Oh, negative, interesting. Wonder if system might be expecting me to plug in that negative answer. So I was wrong about the thrust force being enough. So the module, so yeah, so it must be off the ground already, because if not, there's no way to go down. So if it's resting on the moon surface for some reason, then what it would be is you would have to have basically upward normal force to allow the net force to be zero. But here I think the question wants me to put in a negative answer here. So calculate the acceleration if the fully loaded module was on Earth. It's gonna be even more negative. So instead of this being gravitational acceleration on moon, it'll be gravitational acceleration on Earth, and it'll be even more negative. Yeah, minus 8.94. So can it lift off of Earth? No, it can't even lift off of moon. The way to set up. Yeah. Let me double check, because I don't think this answer's right. So here, I guess it did ask for magnitude of acceleration. I might. Oh, it might be expecting a zero answer. No. There might be a coding mistake in the question. Let's check. 1/6. Oh, I know. So I think in the question code itself, it's probably coded this way. Instead of using moon's actual gravitational acceleration, it's using this divided by 6. Because because with that hint, you will basically have an answer that's slightly different from what I was using, and I think it's different enough from 1%, like different by more than 1%, that the answer I was putting in. So use the hint until that gets fixed. Just use g divided by 6, and that should give you a number that will be graded as correct. All right, let's go to the next question. That took longer than it should have. Okay, it says a rocket sled accelerates at a rate of some acceleration, passengers some mass, calculate the horizontal component of force that the sled exerts on its body. Oh, so here I think, so let me just erase this so it's not confusing to people. I think I can just use Newton's second law directly, because I think the way the question is stated, basically the force from the seat is going to be the net force. So I can just do mass times acceleration. I have the mass, 76 kilograms, acceleration. Oh, I think I can even do this in my head. Let's see, can I do it in my head? Yeah, I don't know. It's kind of a trap for me. Sometimes I think I can do it in my head and I can't. I don't know why I'm blanking on the 6 times 7, 42 I think. Okay. Let's check. Okay, good. Two-digit numbers, sometimes, you know, people make mistakes. Compare this with his weight using a ratio. So here, if I use 10, you know, if I use 10, then I can do this quickly, like 6. But I think that'll be graded as incorrect because it's off by like 2%, you know, 9.8. So I could correct this, so subtract 2%. So 2% of 6 is, I think, a 0.12. So that'd be 5.88, maybe. Maybe it goes the other way. Goes the other way, then 6.12, maybe. Good. Let's keep going. See, calculate the direction. There, the calculation I've done is basically 76 kilogram times 60 meters per second square divided by 76 kilogram times 9.8 meter per second. So, you know, it's not 6.12 exactly, but this is not close enough, within 1% to get graded as correct. Calculate the direction and magnitude of the total force the seat exerts on his body. Interesting. So, we have a horizontal component and we have vertical component. So if I'm drawing a quick free body diagram to make sure I, you know, correctly understand the setup, then on this passenger, there's actually 3 forces, of which we are asked for really 2. So there's gravity pulling the passenger down, mg, and there's normal force from this is the vertical component of the force from the seat that kind of pushing the passenger up. And then this is also actual, so let me call this ny, and this is also technically normal force, but it's nx, accelerating the passenger horizontally. So what the part C is asking for is, imagine adding these two together, then you have your like the combination of those two forces is what they're calling F there, and they're asking for the magnitude and the angle theta here. I think angle presumably from the horizontal direction. So so with that in mind, then so I kind of recognize this right triangle. That's going to be useful in figuring out the lengths and all that. This is the right triangle. I got the 2 legs, nx and ny. So I'm gonna calculate the hypotenuse using Pythagorean theorem. So that'll be so nx, I already have it, 4560. So that's the nx squared plus the ny. I don't technically have it, but looking at this free body diagram, vertically the forces should balance out. So this ny should be equal to mg. So I'm just gonna put that in, mg of 76 times 9.8. That's squared. The whole thing square rooted. So yeah, it's different enough that I do have to take that into account. 4620. 4620 Newton. And the angle, so for the angle, the expression that I like the best is one that says basically this is the opposite side, this is the adjacent side. The opposite over adjacent gives us the tangent theta. And I like to kind of take a pause here. The reason being, so let me first write this out, the opposite, opposite over the adjacent, 4560. So that gives us tangent theta. The reason I like to take a little bit of pause is when you do arctangent arctangent only gives you an answer from minus 90 degrees to plus 90 degrees. And here, with an acute angle like this, just simple arctangent is fine. It's going to give you the right answer. But in those other circumstances where maybe your angle could be in the second quadrant, then you want to be careful about how you interpret the result out of the arctangent. So here, 9.2, that's larger than I thought it would be. 9.28 degrees. Good. All right. I have one more question. Let me get to that and finish this group of 4 questions. Okay, it says a body with a mass of some mass is assumed to be in Earth's gravitational field. So I'm assuming gravitational acceleration is g, 9.8. What is the net force on the body if there are no other external forces acting on the object? Yeah, Newton's second law. So if it's in Earth's gravitational field, A is g, so it should be mg. So if I use g of 10, it'll be 115 Newton. Now I know that will be graded as incorrect because g is actually 9.8. That's off by 2% from this. So let me correct this by 2%. So 2% of this is 2.3 subtracted. So 2.7 maybe. Sorry, mental math is my biggest trap. Whenever I think I can do the calculation just in my head, that's what I want to do. So sometimes it's a trap if I think I can do it but I can't, but here I could. So there it is.